Hey folks, so I'm going to explain the central limit theorem today. And well, let's just look at the definition. I'm at the Wikipedia page. Let's see what central limit theorem says. So basically what it says is that if you have n samples from some distribution, and these are all independent, IID. So the IID stands for independent and identically distributed. So they're all coming from the same distribution. And that distribution has some mean mu and some variance sigma square. So what it says is that if you take a very large such sample, as n approaches infinity, this number converges to normal, right? So Sn here stands for the sum of these x1 to xn. So this is what the central limit theorem says. Right? In other words, if you replace this sum with an average, what it says is that the average converges to the actual mu, and it converges at the rate of sigma square by n. Right? So I'm going to demonstrate what this means on R. Yeah, so I'm just going to use some libraries here. Okay. So let us say I want to generate samples from a uniform distribution, and then I take the average of those samples, right? So let's say I start with a small number, say n equals 10, and I want to repeat this experiment 100 times. So I want to generate samples from a uniform distribution with a equals 0, b equals 1. So if you apply the formula for uniform distribution, the mean is just b minus a by 2, and the variance would be b minus a square by 12. And if you want the standard distribution, standard deviation, you would just take the square root of that. So you get the standard deviation this way. Now what central limit theorem says is that the standard deviation of the average would be this divided by square root of n, right? Because the variance is sigma square by n, so the standard deviation would be sigma divided by square root of n, right? So let me just load what values I expect to see. And now what I'll do is I'll generate the averages. So I'll do this. So this sapply basically just applies a function to the sequence that you supply here. Right? So I'm generating a sequence from 1 to 100, and for each I, I'm just generating n uniform samples of this A and these parameters A and B. And then I'll just take the average of that and return that average. So I'll have 100 averages of 10 samples each. And this will generate a new sample every time. So we will have different averages. And what I want to see is the distribution of that averages. Is it indeed normal? So what I'll do is I'll just run this, and I'll just plot these averages. Yeah, and you can see it somewhat resembles a normal distribution. So this is the density of these averages, the distribution of these averages. And you can see it starts resembling normal, but it is not there yet. I mean, it's not very smooth, right? But does the theorem hold? So these are the expected mean and standard deviation that I expect to see. So mean would be 0.5 and 0.9. So if I just use a fit distribution on these averages and I try say, what is the mean and standard deviation? If this was normal, and it says 0.5 and 0.1. So these are pretty close to what I expect to see. So what happens if I increase this n? That is, if I take a larger sample. If I take a larger sample, create new averages, look at the density, and you can see it's somewhat smoother. And if I do fit distribution, I see, okay, so this time the standard deviation has gone to 0.3, and does it comply with it? Yeah, so it's still pretty close. So this theorem holds. Right? Let me increase n even further. Let me make it 1000. And you can see we are getting a sharper curve. And what I expect is this mean and standard deviation, and does it, what does the theorem say? Close. We are getting closer and closer to the theoretical mean and standard deviation. So let me take a really large number this time. And what I'll do is I'll also increase the number of times I repeat this experiment. 1000. Yeah, so you can see the curve keeps getting closer and closer. If I repeat it one more time, yeah, so this is a very neat normal looking curve. And this is the mean and standard deviation that I expect to see, and what is it actually? They're almost the same. So central limit theorem is actually true. This proves it. But what people often confuse, people often confuse that if I take any large sample, that would be normal. The sample itself would be normal, which is not true. Central limit theorem only holds for sums and averages. So what I mean is if I just plot the density of this uniform sample, this is nowhere close to normal, right? This looks very much like a uniform distribution, which is what it should look like. So large sample doesn't mean normal automatically. Only sums and averages tend to be normal in the limit. So that's the central limit theorem explained. Thank you.